Hi everyone. Today let's talk about session 3.2, sequences and strings. A sequence is a function where the domain is often the set of natural numbers. Okay, so natural numbers are like some notation denotes the positive integers. Some notations include the number 0. Okay, it depends on the textbook and which notation they use. Okay, it can be also considered as an ordered listing of numbers. Okay, definition: a sequence S is a function whose domain is a subset of integers. Okay, we use the notation Sn instead of S of n. Okay, n is called the index of the sequence, which indicates which term. Okay, I have a typo here. Okay, if D is a finite set, then the sequence is finite. If D is infinite, then the sequence is infinite. Okay, it really depends on whether the domain is a finite set. If yes, then we have a list of finite numbers. Okay, if the domain D is infinite, then our list is we can have infinite many numbers in there. Okay. We can denote S or the braces Sn. They are equal ways of denoting the whole set on the domains S1, S2, S3, etc. Sn denotes a specific element in the set. Okay, let's look at example. Consider a sequence where the domain equals 1, 2, 3, 4, 5. Of the sequence S. Okay, if S1 equals 2, S2 equals 4, S3 equals 8, S4 equals 11, and S5 equals -2, then the sequence, we can denote the sequence by 2, 4, 8, 11, -2. Okay? And sometimes we can also put the brace around it to denote the sequence. So S equals the sequence Sn. We have the domain 1, 2, 3, 4, 5. So we have 5 numbers here. We can denote the subsequence by specifying which elements of the domain D which we use. For example, we can have the subsequence Sn where n goes from 1 to 4. This means S1, S2, S3, S4. So the first 4 terms of the sequence. Okay, so that is 2, 4, 8, 11. This is a subsequence. Okay, we can also denote this is subsequent Sn. N belongs in X, where X is the index set. We have 2 and 4 there. Okay, this is another subsequence. So this guy, it means it's gonna be S2 and S4. So we just have 2 numbers in this sequence. Okay, so let's continue. Just keep in mind, so these 2 are different sequence. This sequence we have 4 numbers. This sequence we have 2 numbers. Okay, and what is this guy? Is this guy equals to 4? No, this is S2. S2 is 4, and S4 is 11. Okay, so X denotes the index. Okay, this is the index set. Not the domain, is only the index. Okay, and then 4 and 11. This is the sequence, the subsequence of S. Okay, let's continue. Example: consider the sequence defined by B sub n equals 2n plus n squared, where n is between -2 and 2. Okay, so n is also an integer, okay, between -2 and 2. What is this? What is the sequence? What are other ways of writing it? So in this case, we can have B is sequence B is Bn, where n the index set, or usually the index set could be the domain. It goes from -2 to 2. So Bn is 2n plus n squared, and n goes from -2 to 2. Usually the sequence, we have the positive integers as the index, but according to our definition in this textbook, we allow the sequence, the index, to be negative numbers. Okay, so what is this guy exactly? Well, when we plug in -2, 2 times -2 is -2, 2 squared is 4. 2 times -2 is -4, and then we add 4, we get 0. And then when we plug in -1, 2 times -1 is -2, -2 plus 1 is -1. When we plug in 0, we get 0. When we plug in 1, 2 plus 1 is 3. When we plug in 2, 2 times 2, 4, 4 plus 4, 8. So this is a sequence. We have 5 numbers in the sequence. Okay, next. A sequence is decreasing. So decreasing if for every I and j elements of the domain, if I less than j, then si is greater than sj. Okay, so the relation is like this. Okay, we decrease. Next, a sequence is increasing for every I and j elements of D. If I less than j, then si is less than sj. So it's like this. Okay, it's increasing. Non-increasing means for every I, j in D, if I less than j, then si is greater or equal to sj. So non-increasing. So it's increasing nowhere. Okay, so it could be constant or decrease, but it cannot increase. Okay. Next, a sequence is non-decreasing if for every I and j in D, if I less than j, si is less than equal to sj. Oh, this guy should be in the index, so this should be s sub I. Okay, so it decreasing nowhere, so it could be constant or increase in this case. Okay, let me give you an example. Decreasing sequence. It could be 10, 5, 3, -1, etc. So this is a decreasing sequence. Increasing sequence. 1, 2, 3, 4, 5. This is increasing sequence. Non-increasing sequence, non-increasing, so it could be the same or decrease. Okay? And then non-decreasing sequence, it could be the same or increase. Okay? Something like that. So far, so good, everybody. So it's good to make up some examples, can help us understand it. Okay, let's continue. So let S be the sequence A, B, C, F, F, Y. If R is the sequence A, C, F, R, Y, then R is the subsequence of S. Okay, so you can see we pick this guy, and this guy. Okay, so here's the definition. Let S be a sequence, a subsequence of S. It's a sequence obtained from S by choosing certain terms of S in the same order in which they appear in S. So we pick some terms, but very, very important. We have to make sure they're in the same order. If we flip the order, then it's not a subsequence anymore. Okay, because sequence, unlike set, so for set we learned in chapter 1, the element in the set we don't have order. But here sequence, we do consider the sequence has the order. It's a list of numbers with the order. Okay, the order is really important because it can tell us what's the trend. Sometimes from the first couple of terms, we can derive an explicit formula for the sequence. Okay, next. The sequence BAY is not a subsequence of S because you see BAY BY is a subsequence, but you cannot go backward, you cannot change the order. So BAY is not a subsequence. Okay, and then next example, the sequence 2, 4, 8, 16, 32 to the k is a subsequence of the even integers. So see, this is the even integers, positive even integers. Okay, and then our subsequence 2, 4, 8, 16, somewhere here. This is a subsequence. Okay. Next, if we let n1, n2, n3 be the indices of a sequence S, then the S sub nk would denote the subsequence of S. Okay. All right. I think this I have a typo. I mean subsequence. Oops. Let me move this guy here. Okay. So, which means we have the sequence. Oops. So see. Okay. Okay. There's something wrong with my word. Let me fix it. Okay. Alright, so sequence. We have index S1, S2, S3, S4, etc. This is sequence. Then for subsequence, we can denote SM1, SM2, SM3, okay? Because we also want to count like this is how many terms of the subsequence. That's why we can have M1, N2, M3. Then NK, we know that is the kth term of the subsequence. But N1, N2, N3 are also belongs to the big indexes 1, 2, 3, 4, 5. Okay. All right, let's continue. Example, let S be the infinite sequence defined by Sn equals to n. So where D is the positive integers. So this is a sequence of even numbers. Then we can have S1 is 2, S2 is 4, S3 is 8, 6 and 8. Oh, okay. So this is the sequence, okay, with the index 1, 2, 3, 4, 5, okay. It can be also written as this guy, okay. And then the subsequence defined by 2, 4, 8, 16, 2 to the k. Sorry, typo. Which corresponds to S1, S2, S4, S8, S16. Okay. So here, if nk equals 2 to the k minus 1, then this subsequence can denote snk, where k equals from 1 to infinity. Okay. Alright, so that is the notation of sequence and subsequence. And how can we change the index of the subsequence to be nk? Alright, let's continue to look at more example. Define a sequence by Sn equals 2 to the n plus 4 times 3 to the n, where n is greater or equal to 0. First, find S0 and S1. Well, S0, so we plug in n is 0. 2 to the 0 plus 4 times 3 to the 0, whatever to the 0 is 1. So 1 plus 4 is 5. S1 is 2 plus 4 times 3. 4 times 3 is 12. 12 plus 2 is 14. Okay, and then Sn minus 1, it means whenever we see n, we place n by n minus 1. Okay, and how about S sub n minus 2? It means whenever we see n, we place n by n minus 2. Okay, next we want to show that Sn equals 5 and S sub n minus 1 minus 6 S sub n minus 2. Okay, so we want to show this. Sn, what is Sn? 2 to the n plus 4 times 3 to the n. Okay, so this is also like an island, right? We have this is the left hand side, and we also have our right hand side, and we want to find the bridges to connect them. Okay, so what is the end? The end, okay, so there's one way we can start with the left hand side, that's that, and then we can look at the right hand side. In this case is 5 Sn minus 1 minus 6 Sn minus 2. So we can see what it is. So Sn minus 1, plot this here. Okay, so we have 2 to the n minus 1 plus 4, 3 to the n minus 1, 6, 2 to the n minus 2, 4 times 3 to the n minus 2. Okay, let's see what it is. Yes, so we have 5 times 2 n minus 1 plus 5 times 4 is 20. 3 to the n minus 1 minus 6 times 2 to the n minus 2. 4 times 6, 24 times 3 to the n minus 2. Wow, we can see in order to combine them, we need to split extra 2. So when we split the 2, 5 times 2 is 10. So 2 to the n minus 2. We're going to do that because then we can create the like terms and combine them. Here we split the 3. Then we have 3 times 20 is 60. Then we have 3 to the n minus 2 left. And then 6, 2 to the n minus 2, 24, 3 to the n minus 2. Now we can combine the like terms. Here, 10 and minus 6 is 4. 4 times 2 to the n minus 2. And then 60 minus 24 is 36. 3 to the n minus 2. While 4 is actually 2 squared. And 36 is actually 4 times 9. 9 is 3 squared. Oh, you see what happened? This is, we can combine them. We get 2 to the n, and we get 4, 3 to the n. We can combine, see? And then we can get the left-hand side equals the right-hand side. Then we have proved that. So sometimes you start with this island, and then you know you're gonna end this island. When you want to build the bridges, you can start here and then you go here, or you can start here and then you find the previous bridges until you reach here. Okay, or you can go this way and you go this way until they meet in the middle. Let me see how can I write it so I can show the order. How about I label it? Okay, you can have you find this bridge, and then you find this bridge, and then you find this bridge, or you can figure out what is this and then go back and then arrive to what you start with. This is exactly like this problem, right? We look at the right hand side and then we derive it and simplify, and then we realize, oh, we get the left hand side. Or we can have figure out what's the left hand side and what is the right hand side, and then we show they meet at some point. Okay, so there's three directions. Okay, let's continue. Sometimes it's necessary to find the sum or products of the consecutive terms of a sequence. So we have notation to do this. So sum and products of terms of a sequence. So for sum, we have the sigma. So this is called the sigma. I from m to n. So this is the sum of the subsequence a sub m plus a sub m plus 1 plus da until we reach a sub n. Okay, and for the products, we have this notation. Does it look like a pie? Yeah. Okay, so this is the product, and we multiply all the terms a sub m plus 1 up to a sub n together. Okay, so sum and product. Let's look at example. Let A be a sequence defined by a sub n equals 3 times n for n greater equals 1. Find the sum. Well, this sum means a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, right? What is that? Well, a sub 1, 3 times, so n equals 1, right? 3 times 1 is 3. A sub 2, 3 times 2, 6. 3 times 3, 9. 4 times 3, 12. What is that? 3 plus 6, 9, 9 plus 9, 18, 18 plus 12, 30. So far, so good, everybody. Okay, next, the products. This is a sub, the index start with 3, so a sub 3 times a sub 4 times a sub 5. See, we end at a sub 5. So a sub 3 is 3 times 3 is 9. A sub 4, 3 times 4, 12. A sub 5, 3 times 5, 15. What is this? Plug this in our calculator, and my answer is 1620. Do you have the same answer? Yes? Okay. Let's continue. Remember, for all these examples, you can pause the video and you can try the problems first, and then you can continue to play the video and check your answers. Okay? So suppose S denotes the prime numbers less than 18. How would you evaluate the following? Okay, so I didn't include all the questions here. Let me write down what I'm asking. So what is S then? They are the prime numbers less than 18. So prime numbers are 2, 3, 5, 7, 9. No, it's not. 11, 13. You just go down the odd numbers and see which one is not prime, then don't include that one. Okay, and then we have 15, not a prime, so 17, and this is right. Next number is 19 is greater than 18. So here are the numbers in our sequence. It's a finite sequence. Okay, let's evaluate the following. Let's evaluate this one. I in S, 2 over I. Okay, what is this guy? Well, what does that mean? It means we sum the expression I in S. The first number is 2, okay? And then second number for I is 3. And then so your numerator is always 2. So every time you just change your I by the corresponding term in the sequence. Two over 17. All right, so that is all of them. And then For this problem, you can use your calculator for sure. I want you to calculate by hand. So this problem, let's use our calculator. So 2 over 2 is 1. 1 plus 2/3 plus 2/5 plus 2/7 plus 2/11 plus 2/13 plus 2/17. My answer is approximately equals 2.805569. Okay, now enough. Let's keep that. Okay. You might ask, okay, how do I know how many decimal places I should include? Well, in the exam, I will let you know, okay? So don't worry. Next, let me ask you, I from S to I. Okay, how do you calculate this? Well, first, we have 2 times 2, and then we have 2 times next number in the sequence is 3, next number is 5, next number 7, next number 11, next number 13, next number 17. So it's 2i. You replace I by the terms in the sequence, of course. And let's use our calculator. This is a lot of numbers. And let's plug this in our calculator. 2, 2, 2, 3, 2, 5, 2, 7, 2, 11, 2, 13, 2, 17. My answer is 65,345,280. Oh, such a big numbers, right? Okay, so far so good, everybody. So that's the sequence and sum and products of sequence. Next topic, strings. So in programming, a string is a sequence of characters. So instead of a sequence of numbers, strings is a sequence of characters. For example, the Battles is a great rock group. Okay, this is a string. The string sequence of characters, the Battles is a great rock group, form a string. The double quotation mark denotes the beginning and the ending of the string. Okay. Definition: a string over X, where X is a finite set, is a finite sequence of the elements of X. Okay. So a string can be anything. It's not only restricted to, it could be numbers, it could be letters, it could be words, anything. Okay. It really just depends on what's the set X you defined. Okay. Next, if we let X be ABC, then possible strings over X could be what is. So okay, so there are special strings and ways to describe this strings. Okay, so let X be the set ABC. This lambda, okay, the lambda is the empty string that is called the null string. So null string means nothing. It's like the empty set. Here we have the empty string. So the string which has no letter, nothing there. Okay. AAB is a string over X. So for a string, we allowed the letters to repeat, of course. Okay. So X star denotes the set of all strings over X. Okay, so X star is the set of all string over X. The null string lambda is, of course, in the set of all strings. Okay, because it's a string. And here, A3B4 C to the 4B is a shorthand for the string AAAB CCCCB. Okay, because we have 3 A's, that's why we put 3A cube. And then we have B, and then we have 4C, so we denote C to the 4th B. So we can use this shorthand notation because people think about it. If we have a string that with a lot of repeated letter, you don't want to count each letter, how many that letter repeated, right? So that's why we would like to use the shorthand notation with the exponent. Okay. Next, the length of a string is the number of elements in the string. For example, if alpha is the string A, B, B, A, B, C, 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 then the length of alpha, let's count how many letters are there. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 letters there. So the length is 8. And it can be written as A, B squared ABC cube. Okay, this is a shorthand notation. If alpha is CC ABCC and beta is BA to the 12 C cube B squared C cube, what is the length of alpha and what is the length of beta? Okay, the length of alpha, well, how many there? 1, 2, 3, 4, 5, 6. 6. So we have length of alpha is 6. Well, then B, how many? Well, let's count the exponents. So 1 plus 12 plus 3 plus 2 plus 3. Okay, what is that? 1 plus 12, 13 plus 3, 16 plus 2, 18. 18 plus 3, 21. So this is 21. So far, so good, everybody? Alright, let's continue. What is the concatenations of two strings? Concatenations is the operations of joining character strings end to end. For example, the concatenations of snowball and balls is snowball, right? If alpha equals AACC BCC and beta is C squared B squared A cubed. What is the concatenations of alpha and beta? So alpha beta is alpha AACC BCC and then follow with beta C squared B squared A cubed. Let's use the shorthand notation. So that is A squared C squared and then B. Oh, here this is C to the 4th. B squared A cube. Okay, this is alpha concatenate with beta. How about beta alpha? Well, that's beta first, so C, okay, B squared A cube, and then we have A, C, C, B, C, C. So we have C squared, B squared, well, A, how many A? 5 there. So A to the 5th, C squared, and BC squared. Okay, so this is the concatenations of two strings. Alright, let's continue. Substring. A string beta is a substring of the string alpha if there are strings gamma and delta, such as alpha equals gamma beta delta. Gamma and delta may be the empty string lambda. Okay, so if x equals AB and if alpha is a string, alpha to the R denotes alpha in the reverse order. Okay, what does that mean? Okay, let's see. For example, ACCB is a string, okay, a string. Then let's say this is alpha. Then alpha R is gonna be BCCA. So you just reverse the order, okay? And for substring, let's say beta, let beta be oops, sorry, I think I realized I have a typo here. So let's allow x to be A, B, C. Then then we can have A, B, C there. So otherwise C should not be there. So let beta be C squared Oops. Okay. There's something wrong with my word. Let me fix it. Okay. All right. Okay, so let beta be A, B, A, C, B, C, C, A, B. And then you can see alpha is a substring of beta. Okay, because you see this is the alpha. So in this case, alpha is a substring of beta. Okay, we can also have, let's say, gamma is A, B, C, C, A. So in this case, you can see the alpha in there. Then we can also say alpha is a substring of gamma. And remember, gamma and delta can be empty strings. So that's why here you can have nothing there. So this is still a substring. And furthermore, alpha is a substring of alpha itself. According to the definition, gamma and beta and delta could be empty strings. So alpha is a substring of itself. Okay, so here are the concepts about substrings. And that's it for today. Okay, so please continue to work on your homework, and if you have any questions, feel free to email me or ask me in class or office hours. Have a nice day. Bye.